So today we are going to go over the last thing in this unit, okay, which is projectile motion. A projectile is any object that is moving through the Earth's gravitational field that is unpowered. Okay, a plane is not a projectile. It's powered. There's something keeping it in the air. All right, but anything that is thrown or fired or in any other way kind of shot into the air, okay, is considered to be a projectile, because what's it going to do? Eventually it will fall back down. Exactly. Okay, all projectiles come back down to Earth. Right? Even a satellite is actually a projectile. Right? It orbits the Earth. It's just always falling, but it goes fast enough that it never gets any closer to the Earth. We'll talk more about orbital mechanics when we're in the circular motion unit. Okay, but something that orbits the Earth is actually always falling and is in fact a projectile. Okay, most projectiles that we're most familiar with are things that we just throw. Okay, you throw a ball. Right? It kind of follows that arc. You hit a golf ball, it follows an arc. When you were a kid and you played with the hose in the backyard, right? Okay, and you try and get your friend and they were too far away, so you would tilt the hose up a little bit and the water would go a little bit further. But if you got too far, it started coming back towards you. Okay, the water is a projectile. Okay, anything that travels through the Earth's gravitational field and is attracted back to it is considered a projectile. Okay, there's a lot of things that go into kind of predicting the flight and the distance and all of that. Okay, and that's some of the stuff that we're going to talk about today. The simplest projectile is something that's dropped. Okay, if you drop something, it's a projectile. Okay, if you throw it, okay, horizontally, it's also a projectile. Okay? And we have this kind of fascination with things that travel through the air. Problem is that our idea of how things travel through the air has become skewed. Hollywood has ruined an entire generation of people's minds on how physics works. Okay? There's an incredibly large amount of horrible physics in Hollywood movies. Okay? Like absolutely hideously horrible. Right? Mr. Dickey and I a couple of years ago sat down as one of our projects and we started watching movies. It was a fun project because we got to watch lots of movies, but we started picking out all the really bad physics that we could find. And projectile motion was the one thing we could find the most bad physics on. So I'm going to show you quite a few clips from movies today, okay, that show some good physics and some bad physics and some really atrocious physics. Okay? But we'll kind of look at that from the context of why is this really bad and why did we even believe it when we watched it? Okay? Some of it you're going to watch and go from your generation and go, man, I don't believe that. That looks awful because, well, you're spoiled. CG is incredible. Okay? Back when I was a kid, everything was practical. Okay, if you wanted to jump a car, you actually had to jump a car and film it. Okay, now you just tell some guy sitting in front of a computer, "Hey, can you make that car look like it's flying through the air?" Okay? It's a lot easier. It's a lot less expensive. Okay? You don't have to wreck cars and put a stunt driver in there and all that kind of fun stuff. Okay? All right. So what we have to understand about projectile motion is that it has two dimensions: a vertical dimension and a horizontal dimension, and it's doing both at the same time. Just like the boat questions we did in the vector part. Okay, it's going. There was a component of its motion across the river, and there was a component of its motion downstream. Right. Well, for a projectile, there's a component of its motion that is vertical and is thus experiencing acceleration, and there's a component of its motion that's horizontal and is traveling at a constant velocity. Okay, so those are two things that we need to remember. That is why they are key points 3 and 4. Okay, the vertical dimension accelerates due to gravity. The horizontal dimension moves at a constant speed. Now, obviously, in the real world, it doesn't move at a constant speed because there's air resistance, but we're going to simplify things and work in the utopian physical world where everything is just perfect and easy. Okay? All right. So what goes up has to come down. Okay? Gravity pulls an object toward the Earth while it travels horizontally. Okay? That means that an object fired horizontally will have the same flight time as an object that is dropped. That means this. If I have a rifle that's loaded with a bullet in it and just a bullet sitting beside it, and I fire the gun and drop the bullet at the same time, they'll hit the ground at the same time. How many people think I'm full of it? It's okay to say so. It seems impractical, right? How is it that a bullet fired from a gun could possibly hit the ground at the same time as a bullet that's dropped? Well, I didn't say they would hit in the same place. Okay, they certainly won't. But they have the same vertical distance to fall. They were set right beside each other. And as soon as the bullet is fired and the other bullet is dropped, they're both falling. Okay? And they have the same distance to fall. They fall at the same rate, 9.81 meters per second squared. Therefore, they hit the ground at the same time. Okay? Mythbusters actually did an episode on it where they tested it and found it to be true. Okay? So they proved that it was plausible, is how they always say, but true. Okay? Everyone with me there? Okay? This is something that if you've ever used a firearm, you do have to take into account if you're trying to hit a target. Okay? If you're shooting at a target that's any distance away, you have to account for the fact that the bullet is going to fall as it flies. So you actually have to aim above your target. Same with archery. If you've ever used a bow and arrow, okay, you can't aim directly for the bullseye. You actually have to aim above it because the arrow is going to fall as it travels through the air towards the target. Okay? This is something that military snipers totally have to take into account. How many people have seen the movie Saving Private Ryan? Okay, it's getting less and less every year because it's getting to be quite an old movie. Okay, anyway, in that movie, there's a scene where the whole platoon is pinned down. Incidentally, it was like Vin Diesel's first kind of role in a major movie. They're all pinned down. Vin Diesel gets shot. Spoiler alert, he gets shot. Okay, and the rest of the platoon is pinned down by an enemy sniper that's in a clock tower that's like 800 meters away. Okay, this platoon's own sniper is telling everyone, stay put, because this guy's good. He hit a shot from 800 meters away. He's a good shot. So he starts ranging this shot out that he has to take in order to hit the enemy sniper. And he says, all right, this shot is this far, so it's going to be 2 clicks. He doesn't mean 2 clicks like 2 kilometers. He means 2 clicks of his scope. Excuse my poor drawing here. That's a rifle. I can't draw. Okay. All right, so he's got the scope sitting on the top here. That's what that is. Okay. Now, what he does is he actually clicks the scope, which makes it not looking this way. It makes it aim downwards. So in order to get the target in his sights, what does he have to do to the barrel of the gun? Point it up. So the barrel of the gun is not pointed at the target. The scope is, but the gun isn't. It's pointed well above the target. That way, when he fires, instead of the bullet doing this and missing the target, the bullet does this and hits the target because it accounts for the drop, okay, that the bullet has to make. Everybody kind of follow on that? There's a lot that goes into kind of taking long shots like that. I think I was telling you the other day, the record holder for the longest kill shot, which is a little bit morbid, but okay, the longest kill shot is held by a Canadian sniper. It's almost 4 kilometers. Okay, he hit an enemy insurgent soldier from 3.8 kilometers away. Okay. Now, you can imagine, you can't, like, 3.8 kilometers, like you can barely see that far. Even with a powerful scope, it would be hard to see your target from that distance. Now imagine how far will the bullet drop over that distance? How much will the wind push it from side to side over that distance? Okay. Like it was an absolutely incredible shot. Beat the former record by almost a factor of 2. There is something to be said about the fact that the Coriolis effect could play a role in a shot that long, okay? Because the Earth will actually rotate under the bullet. It's in the air for so long. Okay, so all of that has to be taken into account. But yeah, a little bit freaky in that, yeah, you would never hear that come and never see it come and never know. Okay? That guy is that far away. It actually wasn't his first shot though. Okay? His first shot was short. It hit the ground in front of the person he was shooting at. Okay? His spotter then told him to correct a certain amount, and then he hit him the second time. A little bit scary. All right, that's how we start our Monday off, frightening the living tar out of all of you. Okay, all right, so what we got is something that has sort of 2 dimensions to it. Oh, I drew it already. My gun was better the second time. That one's not nearly as good. Okay, so what I'm going to show you here is, first off, we're going to talk about one type of projectile motion, kind of the easiest type of projectile motion. Okay, and that is something that goes horizontally off of like a, if you're on a diving board and just ran off of it, okay, didn't jump into the air, just ran straight off, okay, or a car that drives off a cliff like in all Hollywood movies, right? Okay, they kind of follow this path. They go, right, and then it seems to be like they're falling straight down and not moving horizontally anymore. Well, they're still moving horizontally. The thing is that their velocity horizontally doesn't change, but their velocity vertically increases a lot, right? They're accelerating vertically. So when they first drive off, what's their vertical velocity? They drive straight off. How fast are they going vertically? 0. Yeah. Okay. If you drive straight off of a cliff, your initial vertical velocity is 0 meters per second, right? Your rate of acceleration vertically is going to be 9.81 meters per second squared. And then let's say that we also knew how fast they were going when they drove off. We'll say that they were moving at 20 meters per second. And let's say that the cliff is 80 meters. How far from the base of the cliff will they hit the ground? What are some things I could find right now, just with the information I have? I could find the time. Okay? If I can figure out how long they're falling for, is that also the amount of time they're traveling horizontally for? Yeah, just like when we did the river questions, right? We had to figure out how long it would take to get across the river, because that's also how long they were moving down the river, right? These things are occurring at the same time for the same length of time, because obviously once they hit the ground, they're neither traveling horizontally nor vertically anymore. Okay. All right, so I'm going to find the time, which means I'm going to have to use this formula. D equals VI times T plus 1/2 AT squared. But VI is 0, so I can just do that. I can solve for how long this thing is going to be falling for. All right, so if I'm going to manipulate for time, that means I'm going to divide both sides by half of A and take the square root. All right, so that's 800 meters. Okay, divided by 4.905, that's half of 9.81, okay, and then we'll square root that. Why did I write 800 meters? 80 meters. Okay, I'm gonna fall for 4 seconds. That's a long time to fall. Okay. All right, 4 seconds is the time that the object's going to fall. So I'm going to write that over here because it also applies to the horizontal part of this. Now, the whole time they're falling, they're traveling horizontally at 20 meters per second. Can I figure out how far they're going to go horizontally? What formula will I use for that? Remember, their velocity doesn't change. V equals d over t. Okay, their velocity is not changing. They're traveling constantly at 20 meters per second the whole time. So d equals v times t, so 20 times 4. Okay, just so happens that they're actually, what are the chances of that? Okay, they're actually going to travel the same distance horizontally as they fall. I think that's the first time that's ever happened. Okay, when I did an example like this, that's almost never the case. Okay. All right, so the key to any projectile problem is to isolate the two parts. Okay, I wrote everything that was vertical over here, and I kept it all together. Okay, I wrote everything that was horizontal over here, and I kept it all together. Because the only thing that the horizontal and vertical parts have in common is time. Okay, everything else has to be treated separately. Everybody okay with that? Okay, there's actually a commercial back in the kind of late 90s. Lexus had this new sedan, sports sedan that was coming out, the Lexus IS, and their advertising campaign was this. This car is faster than gravity. Okay, which is, I mean, that's an impressive claim. So what they did is in the advertisement for it, they took Lexus IS and they put it on the ground, and they took another one and they lifted it with a helicopter to the same distance essentially away, okay? And they said they're going to race them. They're going to drop one, and the one on the ground is going to drive towards the same spot. If the car is faster than gravity, the one on the ground will reach the spot before the falling car. And that would be pretty impressive, right? I mean, it sounds pretty impressive, okay? The thing is that most people don't realize that you can set that up and make it work as long as you put the car high enough, okay? Because in the real world, a falling object doesn't accelerate all the way to the ground. It eventually hits what? Terminal velocity, okay? At terminal velocity, the force of air resistance equals the force of gravity, and the falling object stops accelerating, okay? If you have something on the ground and it's moving through its most aerodynamic dimension, like a car driving on the ground would be, it can go way faster than that number, right? So the advantage, even though it doesn't sound like it is actually to the car on the ground, especially the higher up the car is in the air. Okay, so the car on the ground, as long as you set it up right, should always reach that spot first. Everyone kind of follow me there? But it sounds impressive if you don't think it through, okay? And the way they set up the video makes it look really impressive. So I'll show you that here. It's moving, okay, along the ground already at a fairly high rate of speed. So it has the advantage also because it's already moving. The car that's being dropped is starting from from zero, right? It has an initial velocity of 0, so it has to accelerate, whereas the car on the ground is already moving. Okay, so the advantage is certainly given there. Now, after this ad came out, people said, hey, Mythbusters, you got to fix this. You got to tell us whether this is true or not. Okay, and so Mythbusters ran a whole show. I'm going to show you that now, where they actually tested this whole thing and proved that it's really not all that plausible. So part of the problem with the whole setup of this was when they were initially like doing some test drops, they actually wrecked like 5 or 6 cars before they even ran the experiment. Where's most of the weight in a car? In the front. So as soon as they would drop the cars, they would nose down and they would fall really fast because that's their most aerodynamic dimension. In the commercial, the car fell flat. Well, the only way to do that is to have like maybe a mid-engined car or something where the weight distribution is a lot more even, except that those are hard to find. So what they ended up doing was actually putting weight in the trunk to offset the weight of the motor so that the car would sort of fall flat. But you could see as it was falling, it was doing this the whole time. It was kind of moving around. So it didn't fall perfectly flat. And it would be pretty hard to make that happen, even if they could. So they had that problem. Okay, obviously, they had the problem of the wind making the car not hit in the spot where it was supposed to hit. Okay, but the falling car hit first. Right? Now, part of that could have been maybe instrumentation in the other car. Maybe it wasn't going 105 miles an hour like they thought it was, okay? Or there was slippage because they did this on a dry lake bed, okay? Stuff like that. There could have been any number of things, but in the end, obviously it has to be set up a little bit different. You could definitely get the car on the ground to get there first, just not necessarily with this setup. Okay? That sort of makes sense to everybody. Now, another one, and we'll talk about it here in a minute, it was this thing called the Mega Whoosh. Anyone ever see this giant water slide these guys built on the side of a hill? And then it went up this ramp and shot the guy through the air, and he landed safely in this little tiny kiddie pool. Okay, like, it's crazy. Okay, I'll show you the video in a minute. But, okay, it's good projectile motion. What they had was a guy basically going down this hill and then going off of a ramp and then becoming a projectile where he landed in a kiddie pool. Okay, now that's a projectile that's projected at an angle, slightly different than the one we just looked at where it's just projected horizontally. Okay, in this case, we've got more vector analysis to do. Okay, we have the velocity that he's projected at, which would include a direction, let's say like 30 degrees and I don't know, let's say 20 meters per second. Okay, so we would have to figure out again the horizontal and vertical parts, because obviously this has a vertical component that is accelerated and it has a horizontal component that is constant motion. Okay, so when I look at a projectile that's projected at an angle, I have this side of the triangle, which represents my initial vertical velocity. It's the vertical component of the projected speed. Okay, everyone follow me there, right? Because if I'm projected like this at 30 degrees, I'm moving somewhat upwards, but also somewhat horizontally. Everyone follow there? Okay, so this is really just like solving for x and y. Okay, it's finding the x and y components of that initial projected speed. Okay, x is going to be our horizontal velocity, which we know won't change. That part will stay the same. Everyone following me so far? Okay, so vertically, we know that the acceleration will be negative 9.81 meters per second squared. In this case, I do have to put the negative on because for the first half of the motion, the object's moving upwards. And for the second half of the motion, it's coming back down, right? So I do have, there's a change in direction there, so I have to reflect that. Okay, how would I find VI? I know it's this side of the triangle. Okay, can I calculate it? Yep. Okay, I have to use trigonometry. I'm going to go, since VI or Y is the opposite side, I'll go sine of 30 times 20. Okay, so sine of 30 times 20 meters per second tells me that my initial vertical velocity is positive 10 meters per second. All right. The other thing I can calculate right now is V horizontal. Okay, it'll be the cos of 30 times 20 meters per second. All right, so 17.3205 meters per second. Okay, I want to figure out where I've got to put this kiddie pool if I'm going to live through this, okay? Because I'm going to fly off the end of this slide and then follow this arc, and this is where the kiddie pool has to be, way over here. So I need to know where I have to put it, which means I need to know how far I'm going to travel in which dimension, vertically or horizontally? Horizontally, right? I'm putting it on the ground. I need to know how far I'm going to go horizontally. I mean, knowing how high I go, that would be my vertical displacement. That's also important, but not so much for the placing of the pool, more for like how deep does the pool need to be so I don't die, okay, when I hit the pool. So right now it's just looking at where do I need to place the pool in order to land, at least to hit it. Okay? So I'm looking for a horizontal distance. If I want to find D, what else do I need? Time. Yeah, because we use V equals D over T for the horizontal part. So I need to find time. We said before that the only thing that the vertical and the horizontal have in common is time. So do I have enough information vertically to find time? Right now, not yet. Okay, but there's one other thing. Okay, and it has to do with what we said right at the beginning of class. What goes up must come down. So if I throw something straight up in the air, when it comes back down, if I throw it from here, it goes all the way back, it goes all the way up and comes all the way back down to the same height it left from. So whatever speed I threw it at, that's the speed it comes back at, just in the opposite direction. Reason being, it accelerates at 9.81 meters per second squared downwards all the way up, and accelerates at 9.81 meters per second squared all the way back down to my hand over the same distance. That means that when it gets back to my hand, it's got to be going just as fast as when I threw it. Everybody all right with that logic? Okay. So that means then that VF is negative 10 meters per second. Now do I have enough information to calculate time? I've got VI, VF, and A. Can I find time? Can I use this formula? Right? I have all the information in there except for T, and that's what I'm looking for. So time will be negative 10 minus 10 over negative 9.81. Okay, so that's going to be negative 20 divided by negative 9.81. If you ever get a negative time, you know you forgot a negative somewhere. Okay, on this, shouldn't get a negative time. So this thing is going to be in the air for a total of 2.0387 seconds. All right, now I can transfer that over to my horizontal information. okay, and say that the time horizontally is the same thing. Okay, seconds. Now I can find d. So d will equal v times t. All right, so we'll take that answer and we'll multiply it by the 17.3205. Okay, looks like I need to put the pool about 35 meters away. Okay, is that a long way to fly through the air? Yeah, it's a long way to fly through the air. Yeah. All right. Okay, so I want you to calculate how high a cliff has to be so that a person who runs off the cliff at 8 meters per second would hit the water 15 meters from the base of the cliff. All right, so there's our cliff. We're running off at 8 meters per second, okay, and following a path like that so that this distance here is 15 meters. I want you to figure out how high the cliff is. Okay, give you a few minutes on that, see if you can figure it out. Okay, so first thing we got to do is write down what we know, and we have to separate that into the vertical and horizontal components. Okay, so vertical and horizontal. We know quite a bit of information horizontally. We know that we're moving at 8 meters per second, and that that's not going to change because it's a constant velocity in that direction. And we know that we travel 15 meters. Okay, vertically speaking, I only know two things. What are they? I know the acceleration, and I'm just going to write that it's 9.81 meters per second squared. I don't need the negative here because everything is down in this question. Okay, and what else do I know vertically? If they run horizontally off the cliff, how fast are they going vertically at the beginning? 0. All right, so I know VI is 0. All right, I'm trying to find the height of the cliff, which would be the vertical displacement of any person who jumps off of it. Okay, so I need at least one more piece of information vertically. If I had VF, I could figure out what D is. If I had T, I could figure out what D is. All right, which of those two things can I get from the horizontal information? T. Yeah, I have V and I have D for the horizontal part. All right, so T equals D over V, so that's going to be 15 over 8. So we're looking at about 1.8 seconds or so. And 1.875 seconds. All right, so now we know how long this object or person is in the air for. Now we can solve for D, because as we said, time is the only thing the two parts have in common. So D equals VI times T plus 1/2 AT squared. This is 0, so I'm just going to get rid of that. Plug in my numbers. 1/2 times 9.81 times 1.875 squared. All right, 17.2. Actually, I think we only had one significant figure here, but we won't do that. We'll say it's 17 meters. Okay. All right, so the height of the cliff is 17 meters. Okay. If the question asked, what's the displacement of the person, then what would I have to add to that? Direction, right? I have to say 17 meters down. Okay. Since it asked for the height of the cliff, that's more of a distance. I don't need to put a direction on it. Height implied the direction already. Okay, the cliff is 17 meters high. Okay, everybody all right with that? All right, so that's what we're going to be working on this week. Each day we're going to watch some different videos on terrible physics because we're not going to get to them today. Okay, how many people have seen the movie Speed? It's horrible. Yeah, the sequel's worse. Okay, like way worse. But yeah, so we're gonna watch a scene from that tomorrow. Okay, that's like one of the most, well, not one of the most, one of the least physically accurate movie scenes ever. It's also full of several major continuity / editing errors, which we'll also look for. Okay. Something you should always watch for when you watch TV shows. You wouldn't believe how often they make editing and continuity errors in TV shows. Always watch for it. Okay, couple of reminders here. Okay, you handed in your vector assignments today, guys, but obviously you've got your acceleration lab due on Thursday. Okay, and we got our unit exam coming up on Monday. Okay, I posted the unit exam review last week, so make sure you're looking over that and getting ready for that exam on Monday. Okay. Another reminder here, guys. I've said this several times, but everyone needs to know it as a reminder. When is everything due in this class? Right at the start of class. Okay, if it isn't at the start of class, it's late. So make sure you're all aware of that.